Welcome back to the VEX Isn't Scary project. This is part 3, and we're continuing from where we left off last. Now, we've actually come a long way in the last 2 parts, and we've done some advanced coding. Being completely honest, this isn't a beginner setup. This is quite an advanced setup, and I feel like if you followed along so far, you should be quite proud of yourself. And so, in this part, we're leaving behind the more advanced code, and what we're doing is we're getting into more practical code. So the first 2 parts were to take you out of your comfort zone and show you some, I suppose, scary VEX, but this part is going to show you practical VEX. VEX code that you'll use often and VEX code that is useful and not entirely particular to this project. So what we're going to be doing is creating the geometry that we saw in the render. So it's this geometry over here. And to do that, it's going to require a couple of steps. Right, so in Houdini, we can continue from where we left off last. Inside of this node, we have our attribute wrangle. So we're going to just rename this attribute wrangle to circle setup. We're basically done with it now. We're also going to add some functionality to our code, so let's bring it back up. Press Alt plus E to bring it up. Now, as you may remember, we have our line generation and our point generation. We also have our variables that we've initialized up at the top. Now, one thing that I think would be cool is a variable that allows us to control how quickly this plays back, right? Because currently, as you can see, if we go, it takes 360 frames to complete. That's over 10 seconds. That's very slow. So what I'd like to do is introduce a sort of timescale. So let's create a float called timescale, and we're going to make it equal to the current frame times a channel float. And this float is just going to be called timescale, just like that. And then all we have to do is replace our time that we use over here, so at frame, with this new timescale. So we say timescale, apply and accept. We create our spare parameters over on the right hand side, and with a timescale of 1, it'll play back as it's done before over 360 frames. But if you do it by 2, it will play back in 180. So it will complete a full revolution in 180. And the cool thing is, now we have full control of how quick this moves. So that's a cool thing to have. I'm just going to keep my timescale at 2. And now the next thing that I would like to do is find a way to separate our points from our lines. Currently, it's just one thing. And if we wanted to copy spheres onto our points, which is something that we're going to want to do a bit later, it would be kind of tricky. So a good thing to do would be to add those into groups. So right over here, under our line generation, where we have our add prim, we're actually going to make sure that we can track this. So we call it int prim. All right, we can call it whatever we want. Remember, this is just a variable name. So now this does the same thing as when we do it with the points. It just allows us to track that point number or that prim number. So this is a primitive, and we want to set a primitive group. So all we have to do is say set prim group right over there. And this takes a few arguments. Firstly, the geo handle, which is 0, the name of the group, which we will call lines. Then it wants the primitive to put into it, so we choose prim. Then we put a 1 or a 0 to say either put it in or remove it. So 1 is to put it in, it's saying this is true. And then we just say set. So set it to true. An easy way to think of this is in geometry stream 0, create a group called lines group. If it doesn't exist, it'll create it. If it already exists, it'll add to it. Then we say take our prim that we created, so this over here, and we're saying set it to be in this group. Right, in this lines group. So if we apply and accept and we middle mouse over here, you'll see that prim groups now has a lines group. So we've created a lines group that has all of our lines in it, which makes it very easy to do something like a blast, where we blast away just our lines. So let's also group our points, but obviously those are points and not primitives, so we do that a bit differently. Over here, we can add an int, and we can call it pt2, because we have pt0 and pt1, so pt2, why not? And now what we can do with that is set a point group, and once again, this takes 0, the group name, we'll call this one spheres, and let's add pt2 to that group, and we're saying yes, we want it in that group, so that's a 1. And then finally, we just say set, apply and accept. And you can now take a look. We have a spheres group and a lines group. Perfect. So that now allows us to separate this into two separate groups. You know, we can do two blasts like this. We can do a blast over here that blasts lines, and we can do a blast over here that blasts spheres. So now we have just our lines over here and just our spheres over here. So lines and spheres. Cool. Now let's just decrease the number of lines that we have just so that it's easier to work with. And we're going to go over here to our spheres. Now we want spheres, of course, instead of points. To do that, we can use a copy to points. And the second input is the points that you want. The first input is your sphere. So we're going to drop down a sphere geometry, make it a polygon mesh, plug it into first input. And now we have these massive spheres over here. So we can just scale this down to about 0.15. That should be okay. You know, you can go smaller if you want, 0.1. We've reached the point where it's now just whatever your preference is. So I think that looks fine. Cool. So, you know, this is super basic, but this would be your output for your spheres. So you can output spheres, geo, out, right? And we're going to come back to this and add more functionality to it, but that side, that's the gist of it. That's what we want. So we're going to go over to the lines and just do a few things. So let's convert this to a polywire. Now what we could do is we can actually set our wire radius to be slightly bigger than our sphere's uniform scale. So we can just go over to our sphere, right click on this, and then just say copy parameter, go over to your polywire, right click on wire radius, and say paste relative references. And you'll see that it puts in a bit of code. This is actually VEX code, it's this CH. And we can just multiply it by 1.5. So this is 1.5 times as thick as the sphere. We can then just increase the segments and divisions and do a subdivide with a depth of 3. Once we have this, what we'd like to do is sort of cut it out of a tube. So if we have a tube, let's just drop a tube over here and we'll change it to be on the z-axis and will be a polygon. We'll also increase its rows and columns. So 4 rows, and let's do 30 columns with end caps. So we would want to actually cut this out of the front of the tube. So the other thing that we can do is while this is templated, we can move our tube, set your transform handle, and then choose the move handle. And we can just move this back like that. Just like that. All right, now we have a couple of options here. One option would be to Boolean it. So it would look like this, where you just Boolean subtract, you take your tube and you subtract this from it, and you end up with that. Now, that is one way of doing it, and it's not a bad way. You know, this works fine. You could remesh it or whatever you want from there, and that will work fine. However, I'm going to show you a bit of a different way. We're going to be using some VDBs. So let's do some VDB from Polygon work. So just drop a VDB from Polygons. We're going to convert this to a VDB with a voxel size of 0.005. And then we're going to convert it back to geometry. So convert VDB and then convert it to a polygon. So you have this. What we're going to do on the other side is the exact same thing to our tube. So we're going to copy over the VDB from Polygons and convert VDB and just do that to our tube. Now you'll notice that we have this very faceted edge on our tube. So let's increase the columns to something like 80. And that's better. You know, that's not as noticeable, so that should be good. And the reason I've done this on the tube is actually because I want more geometry to work with. So we went from this, which is something that's kind of difficult to subdivide because it's got a single face on this side with a bunch of quads over here. So if you VDB from Polygons and convert, you end up with a very even distribution of primitives. And this is cool because we can now use this with what we have on this other side. What we're going to do is we're going to apply normals to this over here, and then use those normals to push into this geometry over here. And this is a pretty cool technique, and I use this fairly often where you push along normals. So we're going to use normals over on the left-hand side, and instead of vertices, we'll use points. So if you switch on your display normals, you'll see that we have normals. And what we can do with those normals is transfer them over. So do an attribute transfer, and we're going to transfer them onto our tube. So just like this, normals into second input, tube into first input. Now, of course, this will look weird in your viewport because normals are used for lighting calculations. So when your normals are broken as they are now, it ends up looking like this. So we're going to be taking normals. So just put n on your attribute transfer and we can disable primitives. The other thing that we're going to do is reduce the distance threshold just to about 0.05. That should be good. Now we're going to drop an attribute wrangle, and we can now use the normals that we've transferred to push into this geometry. And you can actually view that we have these normals that have been transferred onto our tube. You can see that they're all there. So we can use those normals and just say v at p plus equals v at n multiplied by a channel float. And we can just call this channel float mult. So that's short for multiplier. Create your spare parameters and set this to about 0.05. And then we can reintroduce normals. So drop a normal node after this, and you can see what it's done. So it's pushed into our geometry quite nicely, but it is very sharp. And so what we can do is we can actually blur our normals. So drop an attribute blur before the attribute wrangle, and we'll be blurring n. We won't pin the border points, and we'll set our blurring iterations to 30. Now it does a really good job of smoothly indenting, right? And the reason I've done this instead of some sort of Boolean or some sort of VDB combine is that this is actually decently fast. If you change this to fewer lines, you can see how quickly this calculates. So, it's perfectly procedural, and that's quite cool. And you can play around with this attribute blur. If you want it smoothed a bit more, you can do that. You can also increase step size, and all of that will help. And let's also increase the size of our tube because, our tube, we're going right to the edges over here. It would be nice if it had some wiggle room. So on our tube, we can just increase its radius scale to about 1.2. And we can also make it a bit thinner. We're wasting a lot of polygons by having it so thick. So let's just decrease the height to about 0.4 and that'll move everything out of place, but we'll adjust it afterwards. So then we can just readjust. So just make sure they line up so that your attributes transfer correctly. You don't want it not transferring because they're too far or anything like that. So that should be good. Cool. So we can drop a null over here. And we can just call this BaseGeoOut. So this is kind of cool because now if we use this with our spheres, you can see that they move together. So let's go up a level. And we can hide this VEX project node and drop two geometry nodes. We'll drop one called base, and we'll drop one called spheres. In base, we'll drop an object merge node, and we'll actually do this for both, which is bringing in that geometry that we created. So in this VEX project, fetch your BaseGeoOut. You have that. And in your spheres, we'll just bring in the spheres that we created. So that would be in VEX project, spheres GeoOut. And you can now start to see that there's some issues and things, but we'll start to fix them as we go. So the first issue that we have is that we can't play this back, right? So you're playing it back and it's very slow. The reason it's slow is because what we're doing here is we're taking this circle setup and we're creating a polywire and a subdivide and a VDB and all of this. But what's coming out of this node is time dependent. It's changing every frame. So every frame, the position of our spheres change, this node updates, and then everything below it updates as well. However, the spheres don't affect our lines, but Houdini doesn't know that. So we just need to drop a time shift node over here just before we blast our lines. And all we have to do is tell it to freeze at the first frame because our lines aren't going to change over time. So on our frame, we can right click and say delete channels and just set this to 1. Now, if we go up a level, it won't recalculate this as it plays and it'll play back a lot more smoothly. Now, the other thing you'll notice is that these don't exactly line up. And the reason is because we've decided to use a polywire over here. As you can see, it stands away from the surface. So obviously our spheres would stay at that point as well. And so we have options. We can just move our spheres so that they line up. So if we just take a look at our spheres over here, we can line them up with the base geometry. We can drop a transform node after we've blasted this. and just move these back onto the surface. So just line them up nicely. Cool. Now another thing you'll notice is that they're extending past the edge over here. And once again, that's also a super easy fix. All we have to do is increase the size of our lines. So we can just transform them up over here. So after we've blasted away the spheres from our lines, we can just transform our lines up to about 1.1. And now it fits just perfectly. And you could even make it bigger, but then you'd need to increase the tube size. So 1.2 and then a tube size of 1.3. And that works perfectly fine as well. So now we have this. So we've started to really optimize things quite nicely, and we've got an effect that looks like it's going pretty well. Now, another thing that would be cool to have is if they weren't just basic spheres, but rather if they were like that render where they have a line in the center that is lit up. So let's just hide other objects, go over here to our sphere, and we're going to make a bit of a change to it. All we're going to do is increase its rows and columns, 50 rows, 100 columns. We're then going to add a group node, just like this, and we're going to rename this to light. You can even rename it to something like light strip. And then what we're going to do is in this base group, we're going to select some faces. So in your viewport, hold space and press 3 to go into your front viewport. Then go over to base group and click on this arrow. This will allow you to add faces to the group. So we're just going to select a thin strip of faces from the middle. So just click and drag and find a selection that you're happy with. Something like that. I think I'm off center. I actually can't tell. I'm sorry if I'm triggering anyone by being off center here, but we'll just do something like that. Then press enter and it'll add those faces to this group. And it will also select faces at the back, because when we select faces, by default, it selects in almost an X-ray mode where it selects faces that are at the back as well. If you don't want that, you just have to click on this eye over here. That will select visible geometry only. So once we have this, we can drop down a poly extrude node. And the group we're going to use is just the group we created, light strip. And we're going to set a distance of minus 0.05. Just something like that. In your viewport, hold space and press 1 to go back to your perspective view. And we have something that looks like this. So this is cool. Now this gets copied to all of our points and we have something like this. And this looks okay, but the issue is that these points aren't rolling, right? There's no physics going on. We're not doing any sort of solving. So there's no actual rigid body physics. So we have to try and fake something. So in here, we're going to do a bit of coding. Let's go ahead into our circle setup. So to figure out rolling, we need a few things. What we currently have are our lines. So we have a line like this. We also have a sphere on that line. Now this sphere moves up and down, right? So it moves up and down. There's two things that we want to do. We want to take this line and figure out the rolling axis, right? So if you can imagine this in 3D, this sphere would be rolling towards us if it's going down and away from us if it's rolling up. But the axis that it's rolling around would be this axis over here. So it would be rolling around this axis. So for this, it's fine. It's pretty simple for the straight up line. And it's also simple for the horizontal line, right? So we have a sphere like this. Then we know it'll be spinning around this axis. It would be spinning like this. But what about one like this, where the sphere is here and the axis is something like this? This is a bit more difficult to calculate, but there is a very easy way to do it. All we have to do is take this value over here and this value over here and subtract this bottom one from this top one. So if this is P1 and this is P2, we just have to subtract one from the other, right? That'll give us a direction. So we'll do P1 minus P2 equals the direction, right? So this is just the direction of the line. But that's not what we want, right? That gives us the direction of this line, but not the direction of our axis that our sphere needs to roll on. To get that, all we have to do is use a neat little function called cross. So when you cross two vectors, you cross the direction and an axis. So we're going to cross the z-axis. So it's the axis leading towards the screen. So we'll do something like 0, 0, 1. Right, so that's what we'll cross. And what that will give us is the vector perpendicular to this. Crossing is extremely useful, and once again, it's one of those mathematical things that I'm probably not explaining as well as I should. So let's say you have the z-axis and the x-axis. If you cross these two, you end up with the y-axis. You just end up with the perpendicular axis. And so it's very useful for things like this. So that's what we're going to be using, and that will give us this direction over here, which we need for our sphere to roll. The other thing is we'll just feed it some sort of rotation. So how much should it rotate? So perhaps it'll do 2 revolutions. And that's easy. We just know that that would be 720 degrees, right? That's 360 times 2. We'll have it so that as it moves along the line, it will rotate 720 degrees along the axis that we find. So I hope that didn't confuse you too much. We're going to be calculating that now. So to calculate it, we're going to go into our circle setup node, press Alt+E. In here, we're going to do a few things. So you can actually add an extra comment over here. You can just comment and call this axis calculation. And down here, we can do the axis calculations. So we're going to say vector axis equals, and then we're going to say line start, right? Minus line end. And remember, these are the 2 variables that we've created before for the start point and end point of each line. So we're just saying subtract the endpoint from the start point. That will give us a vector that we can then use. So we then take that and we say that axis is equal to, and then we do a cross. And we cross axis with the z-axis. 0, 0, 1. Semicolon at the end. And that will give us our axis that we need. Now that we have it, we need to apply it to our sphere points. So like we've done before, where we had this set point group, there's another cool thing that we can do called set point attribute. So we say set point attrib, and in brackets, it works kind of similar to set point group. 0, so your geo handle, comma, the name of the attribute. So we're going to call it axis, comma, the point that you want to apply to. So that's pt2, and the value you want to give it. So we want to give it this axis value. So we apply and accept. And if we want to view what that axis value looks like, we can actually go over here to our visualization, make sure to enable it, then right click on it. And you can just add a plus on your wrangle and choose marker. And the style of marker that we'll use is not a text, but rather a vector trail. And we'll trail axis. And what we'll do is we'll just decrease the length of these. And you can now see that we've calculated exactly what we were looking for, right? This is the axis that our spheres would rotate around. As they roll down this line, they would rotate around that axis. And this always works. So you see over here, it would rotate around this axis, and it would rotate around that axis. So it's pretty cool. You know, it's a simple piece of code. It's very short, but it gives you exactly what you're looking for. The other thing that we said that we would need is to calculate how much it should rotate. But to know how much it should rotate, we also need to know if it's moving. So to know if it's moving, all we have to do is take that progress attribute that we had, so this one that ranges between -1 and 1, and use it over here. So we can just say set point attrib 0, and over here we can just call it rotation and apply it to point pt number 2, and the value that we'll take is that progress value. So we're taking this progress variable over here and applying it to an attribute called rotation. If we apply and accept, you can see that we have axis and we have rotation. Cool. So you can actually hide these element trails if you want by just switching off your visualization. So the next thing we're going to do is we're going to use those values that we just created. So now what we can do is actually just create a float, and we can call this rotation, and it will be equal to our rotation, so at rotation, times, and we said 720, but maybe we'll do 360. We'll see how that looks. And we want this to be radians. So we just do radians over here. So the radians of rotation times 360, that will be our rotation variable. Now there's a reason that I've used rotation here and rotation here, and that's because I want to bring up a point. These two are named the same, but one is a variable and one is an attribute. They actually have no relation to each other. If we had to call this float ice cream, it's the same thing. This code will still work, right? There's no relationship between calling this rotation and calling this rotation. The only thing is that this is the attribute that we created earlier. This is a variable we're creating now. So we're going to do the same thing over here where we create vector axis, and it's just going to be equal to v at axis. Over here, it's important to put this v so that Houdini knows that it needs to call in the whole of axis. If you say just axis, it may bring in just the x component, the first component. So make sure to put a v so that Houdini knows what you're bringing in. In the case of this one over here, let's say float, and Houdini brings in attributes as floats by default. You could also put f at rotation, but it wouldn't really do anything for you. So now that we have that, we're going to do something over here called at orient. Now at orient, I could make an entire tutorial on just at orient, because it goes over quaternions and it's quite an advanced attribute. Just keep in mind that it's a very powerful attribute. It allows you to orient your geometry in a certain way. So what we're going to do here is we're going to say at orient equals quaternion, and all that we're going to put in here is rotation, comma, axis. All that you really need to know about this is we're saying create a quaternion and apply it to orient, right? So orient is a quaternion. It's a vector 4. I'm not going to go into vector 4s in this tutorial. It's something that is beyond the scope of this. So all you need to know is that when you create this at orient, you can use quaternion and feed it a rotation and an axis. It will then create a quaternion that represents rotation around this axis. So we're taking those two values and actually applying it and using it. If we apply and accept and then go to our copy to points, you'll see that they are now oriented a bit differently. And that's because copy to points looks for the orient attribute. Before I play this back, I want you to know that it's not going to look right. And there's a very particular reason for it. But I'm going to play it back and you can see that they're kind of doing this weird little wobble. And the reason is it's because it's rotating around the wrong axis. This sphere over here is set to an orientation of y-axis. If we change it to z-axis, and then try running this back, you'll see that now the rotations look right. They're just rotating in the wrong direction, but generally when you're copying to points, you want to change your orientation to z-axis. That's a bit of an alignment trick, and just keep that in mind. Sometimes when you have it on other axes, they don't work as well as they should. All you have to do is just set it to z-axis and it'll work properly. The other thing that will help this along is by changing our rotation to a negative value. So we say negative of this, and that will flip our rotation, so now they're rotating the right direction. So you can see they're all back and forth. And one other minor fix that we can add to this is to actually just normalize this axis. When we normalize, we're basically evening out the vector. Now, when you're working with axes or normals, then a normalize is very useful. So just put a normalize just like that and normalize this v at axis. It'll make a very slight change, but it's actually a good practice. Just normalize your axes and normalize your normals. So if we go up a level and take a look at this over here, you can see that they now roll up and down. And it looks pretty good. You know, the rolling looks correct. And it's going on the right axes. And we can still increase the number of lines. And everything still works correctly. So a quick recap in what we did here. We learned how to add groups by using the set prim group and set point group. We also learned how to set attributes using the set point attrib. We learned a bit about crossing vectors to find the perpendicular vector. The other thing that we did was we used a rotation and an axis and created an orient attribute to rotate around an axis. And over here we learned how to push along normals. All in all, it's a couple of very useful techniques that you might find yourself using more and more often as you go along. And of course, each one gives you a lot of control. For example, by pushing this value up or down, you can control the indentation, as opposed to using something like a Boolean, which would be a lot slower. So yeah, you know, that's all for this part. In the final part of this series, we're going to just be rendering this out. So there's going to be a few more things that we're going to do. We're going to play around with some color stuff, and I'm going to talk about how you bring attributes into shaders. And that's going to be the last part for VEX Isn't Scary. So once again, I hope that this wasn't too much to take in. If it was, I hope that you'll try going over it again, and hopefully it'll make more sense the second time around. But if it doesn't make any sense, feel free to contact me or feel free to drop a comment down below, and I'll try to address any concerns you may have. So thank you once again for watching, and I'll see you next time. Bye.